Running rapidly to part 2 of this chapter number 3 on CCNA cybersecurity operations with me, Joachim Kjærestad from the University of Skövde. And where we left off was after having an overview of Linux, and now we will move on to a few slides on Linux administration. And where we will begin is with configuration files. Linux services are usually managed using configuration files, and configuration files are usually essentially a listing of configurable parameters. So whenever you want to configure a service in Linux, you will change parameters in a configuration file, and when a service is started, it will load the configuration file and adjust itself according to the configuration. And I just tell you this because you should know that whenever you need to modify a service in Linux, you usually need to find the correct configuration file. Unfortunately, there is no common rule for how configuration files should be formatted, but usually it lines that says option equals value. So for instance, port number equals 22. And you usually use the hash sign for commenting. So if you want to add commenting, you start a line with the hash sign. So rapidly from configuration files to device hardening. And device hardening is basically about a term used to describe practices we do to ensure the security of a device or increase the security of a device. So the best practices for device hardening, as stated by the CCNA cybersecurity operations material, is that first of all we need to ensure physical security. You can usually say that if someone gains physical access to your device, then it's game over. So you need to ensure that the device is physically safe. If we're talking about servers, they should be in the server room that should be locked from, so that no one without the right privileges can access it. You need to keep track of your laptop, stuff like that. Then you should minimize installed packages, and this comes back to the principle of least privilege. You can apply that here as well. You shouldn't have more stuff installed on your machine than you actually need. And the reason for that is because you should treat every single thing that you install as a possible attack vector, something that can be exploited by an attacker. Whenever we install something on our machine, we add more code to our machine. That's essentially what we're doing. We add more code that can contain errors. The same goes with services. If there are services we don't use, we disable them. We use SSH for remote configuration. SSH is a protocol that allows us to access a device remotely. And it's a secure protocol because it sends traffic encrypted. However, we should disable the ability to log on over SSH using root. No one should be able to access a device remotely as root. And root, if I haven't mentioned it before, is the administrator account in Linux. Keep the system updated, of course. Disable auto detection of USB devices. So, for instance, you may have heard about road apples, where people place devices such as USB devices in a public area and just hopes that someone is curious enough to pick it up and plug it into their computer. If we have auto detection on, there is a fair chance that the device will automatically be detected, and there may be an auto-run file on the USB drive that installs malware on our device. So make sure to disable USB auto detection. You should also enforce strong passwords. I don't want to say too much about password security because I know that my view is not the same view that is given by this material, but in some way you should enforce a policy that makes sure that 123 is not an okay password. You should force periodic password changes. This is something that is said by the CCNA material. If you read the NIST standards, that is actually not something that is used anymore. Instead, you should change passwords whenever the passwords are compromised, not more than that. And the reason for that is because when you force people to have too complex password and you force people to change them ever so often, they tend to choose weak passwords as they can. So if you start with wanting the password summer and it says, okay, summer, you need to have a capital letter in it. Well, then you type summer with a capital S. Then it says you have to have a number in it. Okay, so you go, okay, capital summer 1. You need a special char. Okay, capital summer 1 exclamation mark. And then the number just increases because you can't reuse old passwords. A way that I would enforce is to have a password policy saying that you should combine 4 or 5 words. If you don't believe me, send me an email and I will send you convincing research in return. Okay, leaving passwords. Know that this material wants you to enforce strong passwords, force periodic password changes even though it's wrong, and you should also keep users from reusing old passwords. Moving on to log files. Just as with Windows, Linux will use logging to monitor events such as failures, installed devices, failures, I mean logon failures of course, and also various security information. You can find log files in Linux in some different ways. The more historical way that still works in many distributions is to just find the logs as text files that are usually located under /var/log. And those are basically plain text log files that you can read using cat, head, or tail. You can use the command dmask, which will display the kernel ring buffer, and this typically includes messages produced by device drivers, so many hardware-related events, for instance. A third way is using the command journal_ctl, and this is used to display log files from the logging service called systemd, which is a system and service manager you find in modern Linux distributions. Some of the log files that you want to be aware about is varlog messages that contain generic computer activity logs. Then you have auth.log that contains authentication related events. If you are running a Red Hat or CentOS Linux distribution, you'd find the authentication related events in varlog secure instead. And there is one called varlog boot.log that contains messages recording during the boot process, and many, many more. So if you install some software like Apache web server, that software may create its own log files. And you should note that different Linux flavors, different Linux distributions may log to different log files. This is actually a very good time to do lab 3.2.1.4 to get a little bit familiar with Linux log files practically. So you go do that and pause me for a little while. I know I sure as hell would like to, but I am just moving on to file systems. So the thing with Linux is that there are usually many different ways to do things. And there are many different file systems that can be used depending on need and purpose. And some of them are these listed here. So first we have ext4, which is the most commonly used Linux file system today. Then we have NFS, Network File System, which is a network-based file system that allows file access over the network. And then we have the swap file system, which is actually not really a file system, but a special partition. Remember that a partition is a logical part of the hard drive, and the swap file system or the swap partition is used for memory paging when the computer needs to address more memory than what is physically available. When that happens, it will store parts of the memory in the swap file system. I also, on the topic of file systems, want to mention master boot record, MBR, and GUID partition table, GPT. This is something that stores information about how the system is organized, for instance, the partition table. So the MBR or GPT will store information about how the drive is partitioned, and whether you use an MBR or GPT partitioned drive, this information will be stored in the beginning of the hard drive. Moving on to rules and file permission. So file system permissions are used to determine access to files and folder. And this is of course something we need because in a multi-user system, different users should have access to different things. In Linux, we can set permissions to users and or groups that own a file, or others. So we can set one type of permission for the user that owns a file, one type of permission for the group that owns a file, and one permissions that goes for everyone else. So if you look at the bottom part here in the slide, this is actually permission where I tried to do some white lines to explain the different parts of it. So if we look at the very first part here, which is in this case, yes, the dash. This shows the file type, where a dash is a file and it can be a D, meaning that this would be a directory or folder. Part 2 here is permissions for the user owner, the user that owns this file. And the partition bits that can be set, there are 3 of them, are read, write, and execute. I'll describe them next. So when it looks like this, we have RWX. That means that the user owner of this file have read, write, and execute permissions. And the third part, this part here, is the permissions for the group owner, the group that owns this file. And in this case, it's read and write, so the group owner has read and write access. Finally, or in the fourth part here, we have we have the permissions that are for everyone else. So everyone that is not the user owner or part of the group that owns this file will have read access to this file. Then the one will skip that. Next we have the name of the user that owns this file. So James is the user account that owns this file. Next we have the group owner. So user is the group that owns this file. And the final part I want to highlight here is the file name, which is very last. So that are the permission bits, and what they actually do is, well, R is read, W is write, and X is execute. Read means that you can read the contents of a file, open it, or if it's on a folder, it means that you can list the contents of a folder. The write permission means that you can write to a file, write new data to it. Or if it's set on a folder, it means that you can add, remove, and rename files in the folder. And execute means that you can execute a file if it's an executable, and enter a folder if it's a folder. So that's permissions briefly explained. That was all for this lecture. Feel free to leave comments in the comments field. See you next time.